Welcome to Centrails, a case study with focus on using the MicroMap. If you haven't already done so, we suggest you do the MicroMap exploration with Cell Designer tutorial first. We'll explore hydrogen sulfide, or H2S, one of the key gases behind the smell of flatulence. Most of the gas we release is actually odorless: hydrogen, carbon dioxide, methane. It's the trace gases, less than 1% of the volume, that give farts their scent. And among those, hydrogen sulfide is the smelliest. H2S is produced by the gut microbiome, and it's been linked to both health and disease. In this tutorial, we'll use the MicroMap to investigate H2S metabolism. We'll start just by looking at the MicroMap in Cell Designer. First, open the map and search for hydrogen sulfide. To do that, open the Find Species window with Ctrl F and type in its VMH abbreviation, which is H2S. Make sure you're searching by name, not ID. Also, we want to find all versions of hydrogen sulfide, for example inside a cell or outside, so set the search to begin with, then click Show All. Highlight them by using the Change Color in Shape function. Make the shapes larger and choose a bright red. Now every H2S molecule is immediately visible across the map. If we zoom all the way out, we can see how these H2S molecules are concentrated around certain areas. Let's start exploring the sulfur metabolism section. You can click on any reaction arrow to see its name in the notes panel. To make the map easier to follow, we'll recolor those reaction arrows using the Change Color in Shape function as before. For example, choose a bright red line with a bold line width. That way the direct H2S reactions really stand out. Next, let's trace the wider pathways that H2S participates in, both upstream and downstream. To keep them distinct, use a different colour, say orange, for those reaction cascades. Now, what can we see biochemically from this inspection? In the sulfur metabolism section, we see a split: an organic side with carbon-containing metabolites and an inorganic side with sulfur-containing ions. Moving into the neighbouring methionine, cysteine and serine metabolism subsystems, we see repeated amino acid transformations: cysteine to pyruvate, cysteine to serine, homocysteine to cysteine, and acetylserine to cysteine. All of these involve H2S either being produced or consumed. So even with just Cell Designer, we already get a systems level view of how H2S is integrated into broader metabolism. A quick way to check whether a specific microbe can perform H2S metabolism is to open its reconstruction visualization and highlight the H2S molecules, just like we did earlier. If a H2S node connects to one of that microbe's highlighted reactions, then the microbe can perform that reaction. For example, if we compare D-sulfovibrio desulfuricans with Lactobacillus pasteurii, the difference is obvious. D-sulfovibrio has many H2S linked reactions, whereas Lactobacillus has none. This kind of inspection lets us quickly see which microbes are active players in H2S metabolisms and which are not. So far we've worked directly in Cell Designer. Now let's bring in the Cobra toolbox for more advanced analysis. First, place the MicroMap XML file in your working directory. If required, initialize the Cobra toolbox and set to your solver. If you don't know what I'm talking about, please go to opencobra.io website and follow the installation instructions. The first step is to parse the MicroMap into MATLAB by using transform XML to map. When we do this, the Cell Designer file is split into two parts, XML and map. We'll only use the map part for our visualizations. Those parts can then be recombined with transform map to XML to create a Cell Designer file, which you can open in Cell Designer for exploration. The MicroMap has its own default color scheme, but sometimes you may wish to start from a more neutral version. Using the Unify Metabolic Map CD function, we can reset all metabolites to white and all reactions to grey, so the map becomes a blank canvas. Next, we want to highlight the reactions involving H2S. To do that, we first need to know which reactions include H2S as a reactant or product. As we are looking at all the microbes collectively, we can query the VMH database. Don't worry about the code details if you are unfamiliar with Cobra. Then we can use the modify reaction metabolites function to highlight H2S. and all the reactions it is involved in. The result is a map where every H2S linked reaction is emphasized. This mirrors what we did manually early in Cell Designer. With Cobra, we can generate reconstruction visualizations from scratch. Let's focus on D-sulfovibrio from earlier and lactobacillus. Download their reconstructions in mat format and place them into your folder alongside the MicroMap. Then run the visualize reconstructions on map function. You will get a visualization for each reconstruction. Now parse those visualizations so we can highlight the H2S nodes. Change met color will change the color, change nodes area will change the size. Stick your maps back together into Cell Designer format, and our D-sulfovibrio has many H2S nodes linked to its reaction content, while lactobacillus has none. Now, H2S itself is a widespread metabolite, so the lactobacillus pasteurei case is somewhat special amongst microbes. So how widespread is H2S metabolism across different lactobacillus species? Let's create a heat map. Download all lactobacillus species reconstructions and place them into a new clean folder along the MicroMap. Generate their visualizations using visualize reconstructions on map, and then run visualize normalized reaction presence to generate a heat map. Highlight the H2S nodes as before, and then reconstitute the Cell Designer map. Looking at our heat map in Cell Designer, we can see that indeed H2S metabolism is rare amongst the tested lactobacillus species, as judged by the blue lines. Finally, let's take things further and look at visualizing results from flux balance analysis, or FBA. Let's focus on D-sulfovibrio, place its reconstruction alongside the MicroMap in your clean working directory, load the reconstruction using readCB model, and parse and decolorize the MicroMap. FBA allows us to simulate the maximum secretion of H2S. In Cobra terms, we therefore need to set the objective reaction with change objective as the H2S exchange reaction, and prevent H2S uptake by setting the lower bound to 0 with change reaction bounds. This means we are now only secreting H2S. By default, exchange reactions are wide open, which may cause unrealistic results. So let's define a list of exchange reactions for major sulfur donors and set their lower reaction bounds to something more physiologically relevant, like -20 millimole per gram per dry weight per hour, which is the FBA unit. We can now run FBA by using optimized CB model. The resulting flux distribution can be visualized on a MicroMap by using the add_flux FBA function. Remember, the flux value is unique, while the flux distribution may not be, because the system of linear equations is underdetermined. Note how the flux distribution spans many different areas, well beyond sulfur metabolism. All the color reactions carry flux, such to maximize H2S secretion under the given conditions. We can also compare different conditions. For instance, let's run one scenario where the microbe only has inorganic sulfur compounds available and another where it gets cysteine and methionine. So let's define the subgroups containing the exchange reactions for the desired compounds, inorganics versus cysteine methionine. We can then simulate and compare the maximum H2S secretion with different sulfur sources by using FBA and visualizing the results on the MicroMap. We get the highest secretion potential of 200 millimoles per gram per dry weight per hour with all sulfur sources involved. About half that with only cysteine methionine derivatives as sulfur sources, and then 60 millimoles per gram per dry weight per hour with inorganic sulfur sources. The associated distribution changes as well, with no fluxes predicted in the sulfur metabolism section for cysteine and methionine sources, yet there is flux with inorganics. Notably, using inorganics as the only sulfur sources, we simulate that a cysteine producing reaction carries flux. That particular reaction does not carry flux in the cysteine methionine case. However, a reaction synthesizing thiosulfate does. This observation highlights that the interconnectedness and redundance of reactions, balancing substrate availability with thermodynamic constraints. And that's the end of our case study. We've used the MicroMap to trace hydrogen sulfide metabolism step by step, first by manual inspection in Cell Designer, then programmatically using Cobra. Along the way, we've seen how some microbes, like D-sulfovibrio, are major H2S producers, while others, like lactobacillus, barely contribute. Of course, there are many more ways to integrate the MicroMap into your workflow. Have fun exploring, and we are looking forward to learn about your creative exploits.